Hello everyone, this is Richard from SimScale. Thank you for joining to today's webinar about design and analysis of heavy machinery and agricultural equipment. Before we start, let's check if the audio works. So please could you give me a hand if you can hear me? Nice. I see a lot of hands. Great. Okay. Good. So we're ready to start. Okay, so first a little bit just introduction about myself. So my name is Richard. I'm here at SimScale, senior engineer. Mainly I'm dealing with salt mechanics, also heat transfer. Whenever you, after the webinar, have questions, you can directly write me an email. My email is here, or also use my Twitter handle to get into contact with me. Okay, so let's start. So today we want to go through a usual or some design scenario which you would see actually in if you design heavy machinery, where you have a specific initial design, maybe you have an initial problem, maybe not, and now you want to see or assess the performance of your design already in an early stage before you build a prototype and before you actually had to spend a lot of money to build a prototype, to test it, and just to get to know that there should be some obvious design improvements that could be very easily be shown by doing some initial simulation on your initial design. So in today's example, we're trying to optimize a loader arm of a backhoe loader. So what we see here in orange is the actual assembly, the part of the assembly which we want to tackle today. So we got a design from GrabCAD user Sankar Ram. Thanks for that. It stated this design is based on an actual JCB loader. So maybe we're close to that. So what are the design objectives here? How do we improve the design, or what is our objective for this example case here? Of course, under load conditions, we want to assess the strength of the design and also want to get to know how it behaves under misuse conditions. Under all conditions, you want to ensure that there is no permanent deformation, obviously, on the design. So no failure from that end will occur. Usually we assume a factor of safety which has to be taken care of, which means the maximum stress that we're observing during the simulation should be lower than the yield limit by a factor of at least 2. The higher the better. But usually also on the other hand, it means the higher, if our factor of safety is too high, probably we used too much material on a specific part and should be able to reduce the weight of the part and the material to obviously save money during for the build, but also one important factor here is obviously also fuel consumption during operation. So maybe fuel consumption can be reduced by a few percentages if you reduce your overall weight in the same range. Okay. Besides these extreme conditions where we consider yielding, so permanent deformation of our structure, one other aspect is usually the endurance or the fatigue lifetime of the component. For this structure here, we are using, or it's basically made of steel, and there the the yield limit and the endurance limit are usually pretty close. So for the example today here, we are only considering the yield stress and designing with regards to the yield stress as a reference. Yes, so on the right side you already see colored the assembly that we are using today. We have the main part here in blue is the bucket bell crank, which is the heaviest part here. But then we have also several linkages, and we are trying to optimize basically the weight with respect to still being in the limit of our stress conditions. Yeah, so let's first see what should be usually what we actually used as a model that we use for simulation. First of all, you see we only modeled half of the design. In most cases, you can assume that we have a symmetric load condition here, so we can only use half of the model. This saves us obviously computational time, and we get the results faster without losing any accuracy on the results. In some cases, it also eases up the simulation setup, but here the main reason is that we save us some unnecessary computation time. So on the left side, where the bucket would be attached, we directly apply the loads, depending on the load case, either the operational load or the misuse load. We'll have some hydraulic constraints on the lower side, and we have a pin constraint on the end on the right side. So basically what we're trying to do here is shortening the traditional design life cycle that you usually would have. Usually you have an initial design, the design that we're speaking here about. You will build a physical prototype, you will do the load test on a physical prototype, then assess the failures that you got, the results of the tests. Sometimes you basically fail to measure basically at the right locations, so you would have to redo the test, put your measurement points to different locations where they make more sense, where you have the extreme, like the failures, for example, where cracking appears, where the highest deformations appear. And then based on your measurements, you can have some informed design decision where you iterate once more with an updated design and build a new prototype. And this cycle usually is very lengthy. It's very costly. Each prototype, depending on what you're building, is extremely expensive. Certainly those parts that we're speaking of here are very expensive to build a prototype from. So we're trying to reduce the cycle here, and also not only the time to production, but also the overall cost. And this is done using simulation, where we quickly can iterate over multiple design iterations, and also, as important, to get an impression on the results of the performance of the design over the whole domain. So usually if you're doing physical testing, you have specific discrete measurement points on your prototype. When you're doing a simulation, you have the results on all the points of your design. So you're not restricted to a specific point where you measure whatever quantity of interest you have, but you can have it on the whole design. Yeah, of course, if you shorten the product cycle, development cycle, you can also save a lot of money and bring your product to market faster. And where we are different than the traditional simulation tools that you probably already know of, or maybe some of you already have used, is that SimScale can be started and be used and give you the results pretty easy without any initial startup time. So you can just sign up, upload your model, measure it, analyze it, and get your results in a very short amount of time. You don't have to think about your computing capacity. You can use a simple laptop. You can use it on any device you want. It's accessible from any hardware, even from your mobile phone. The computing power that you use is not restricted by your device. So we're doing all the computations on the cloud. You can do multiple simulations in parallel, as many as you want. SimScale is built with a pricing model that is very cost efficient. So you have very low entry prices where you can start already with simulation, and then once you need more capacity, more simulation power, you can upgrade on demand to higher values here. So what also is interesting that we built SimScale with having in mind that simulation should not only be something for a simulation expert, but every designer should have access to simulation and should be able to analyze his design. So we built a lot of functionality into enabling collaboration with other engineers, with our support, with a large community of users that are willing to help any new designer starting to use simulation. And this is really something that puts SimScale apart from other tools, that you have this instant access also to the knowledge of thousands of or hundreds of thousands almost of other engineers that are willing to help, and you have the instantaneous support via our live chat. So whenever you do another simulation and you hit a roadblock, you can just ask support for help, and they will directly have a look at your project. You can directly share it and get to the solution pretty fast. So from the capability side, obviously we have a pretty complete FEA package on the platform. You can do static stress analysis, also all kind of dynamic simulations like transient dynamics, harmonic vibrations, frequency analysis, eigenmodes, but also thermal simulations, any kind of nonlinearities like contact with friction. You can use several parts, you can use assemblies, and we have various material models available with, for example, elastoplastic materials, creep, several others. But SimScale is not only a tool for structural mechanics. You can also do CFD analysis. You can do any kind of fluid dynamics simulation, single phase, multi-phase, with heat or without, incompressible or also compressible simulations. And there are even more in development. So let's have a look actually on the platform to see what I'm talking about here. So this is the initial design that we directly uploaded on the platform, where you see the different parts colored. And the first step that you would usually do, and it's pretty simple, you create a mesh from this design. We have several meshing algorithms available, and here for structural mechanics we use the automatic tetrahedral algorithm, where you simply select the fineness of your model, and that's it, basically. You can use higher order elements, first or second order, and the difference from SimScale to other tools is basically here is where you're choosing on which machine the simulation is running on. So I can have a simple 4-core laptop but still run my meshing job on a 32-core cloud instance with over 240 gigabyte of RAM. So what we can do is we just quickly create a new mesh. The default settings are okay, and once we're clicking on start, basically you will see that here the operation is already started. We could now close the browser, do anything else. The meshing is computing, and basically it's going into the queue, is starting up a cloud instance, and is firing up the meshing there. The next step, once the meshing is done, we basically create our actual simulation setup, where we have multiple simulation analysis types that you can choose from for solid mechanics, static, dynamic, several more. And once you create the new analysis type, basically we prepare a set of input parameters for you which makes sense, and you only have to fill out what's absolutely necessary to get your analysis starting. So once we did that, we can assign the proper mesh that we want to analyze and assign the materials. As an example, we can do that here. So this is our assembly. As a material, we import from our library a simple steel. And basically, as all the parts are made from steel, we assign to the complete assembly with one click, and we're done. So simple as this, the whole other setup steps will go. You just work your way from top to bottom, add constraints. For example, you can add a fixed support here, and so forth. We won't go through the detailed setup right now, but this is the whole idea of the setup. That's very, very easy and very quick. And the same as for the meshing applies here. You create a new simulation run. Of course, we got a warning that we didn't define contacts, and you define basically on which machine it is running. And as a last step, what you also do is, once your simulations are done, you can load the result into our post-processor, into our online post-processor, and post-process the results there. I already did the post-processing and the setup, so let's directly have a look back at the presentation. Okay, so we gone through the actual steps, how we would set up an end-to-end design analysis on SimScale. And now basically what we have is our initial result, where we see how our component performs. So in red you see the areas where we have very high stresses, and blue we have very low stresses, where you could potentially reduce material on that part. And equivalently, we have the factor of safety calculated here, where red means we are very low and should improve there, and blue means we have a safe design and can already remove material. And here we see it's almost completely blue, so we are good here and might reduce the material to improve the overall design efficiency. So here we have now 3 design options, or 2 additional options which we would take to the test here. So for design number B, we reduced the thickness of several members here to just save material. But actually after we did this, now we have no idea if maybe we reduced the material too much, so our design might not be safe enough. So how would you usually do that? Build a prototype, measure the performance, see if it still withstands the load or not. Here we're doing it pretty easy with the simulation. And another design option would be to simply cut out here the material from the inner side, and maybe this is already good enough to still withstand the loads. but significantly reduce the weight. So as we already did our initial design, here we got to the meshing of those of those three cases. It is pretty easy to just plug in a new geometry, use the exact same setup that you had before, reattach your loadings and your constraints, and run the simulation as quickly as in half an hour for both new designs. So within that investment of one additional half an hour, we got these new designs evaluated. So what we're seeing here on this slide is we now have the von Mises stress, or the equivalent stresses, on our new loader designs. So we see that design number B already has a lot higher stresses on this bell crank, and design C seems to be a little over the top here with the stress. So probably we're gone too far here. So let's have a look at the results of the factor of safety, where we see that for design B we are in the range of a factor of 5 on this area here, whereas on design C we can already see that our factor of safety is well already below 2, so we should not go that far and reduce here that much material. So if we actually get the data not only visually but looking at the numbers, we see that design A has about 36 megapascal of stress in the operational load condition, and if you put up a misuse load of like about 20% on top of the maximum operational load which we defined, we still are in a very safe region. And the same goes for design B. We only increased a little bit in the stresses and are still safe. For design C, we can already see that we are very close to the yield limit of 250 megapascal. For the operational load, not yet, but already for the misuse load, we are too close. If you're having a look at the factor of safety again, we see that for design A we're pretty good, already too good. So 5.7 for the misuse load, which is basically very safe for a misuse case, and it points us to the case that we added too much material here and are basically wasting money. Design B has already a much better range for the factor of safety. And design C, we can see that 1.3 is really close. We already have to factor in that our simulation results are probably not 100% accurate, so there needs to be some additional safety factor applied. So 1.3 is definitely too close. Even 1.5 is questionable. So to be above the threshold of 2, we should, from these design explorations here, choose design number B. But basically this could be one option, that we already have these two designs evaluated and see, okay, design number B has the best compromise between reducing material and still being in the limits for safe operation and a long enough operation lifetime of the wheel loader. Another option would be to now actually use the results of the design number B and C to further improve it. So if we start with design number C, we can see that here in the linkage or in the bell crank, we should revert to design option B here, but on the rest we see that we can still use option C's design here. Maybe also in this area near the bucket further reduce material. So we might want to check a design number D and have a next iteration to check on if we could improve the design significantly. Yes, to have the overall view here, to give you an idea on how much investment this whole result investigation or the whole investigation of the design would take is basically 2 hours approximately for the complete setup of all 3 cases of manual engineering time. Most of the time goes into the initial iteration where you have to set up the initial simulation settings, and then each consecutive design iteration is in the order of minutes. So 2 hours in total, 3 hours actual computation time for all 3 designs, where we have in each design 2 load cases. So it was roughly 20 minutes computation time per design per load case. So what we got in return is if we base our results on design number B, that we saved about 6% of material in this huge example here. This is already 250 kilogram of steel that we can save here without even touching the actual topology of the design, just reducing some thickness. And what we already also got is further hints where we can, in which direction we can improve our design, which can be used for further iterations. Yes, so if you also want to improve your design of your machines or whatever you're working on, there's actually only two steps to do. Sign up on the platform and schedule a demo with one of our engineers where you can, on your specific application, explain how the simulation setup would work, how SimScale works, how the results would look like, and get your specific case solved to see how much you can benefit from actually using SimScale. Yes, so we're at the end with our webinar today. If you have questions, I guess we still have 1 or 2 minutes time for you to ask questions, and I'm happy to answer those. So feel free to post any questions you have. Okay, so far no questions. Waiting a few more seconds here. If we still don't get any questions, as I've showed in the beginning, if you want to post a question later, just write me an email or approach me via Twitter. I'm happy to help. Or you can also contact us directly on the platform, contact support, or ask questions in the forum. Good. Okay, so no further questions, then no. Then we're good here. If there are further questions, again, you can mail them. And thanks for watching the webinar, and see you soon on SimScale. Hope you enjoyed it, and thanks again. Thank you.